As human beings, we are instinctively drawn toward the grandeur of the natural world, to spectacular displays that inspire us with their magnitude and power. Wonders of rare beauty and complexity, creativity and design. Wonders born on the gossamer wings of an insect, weighing less.
As you watch a butterfly, to describe what you're looking at, you can't really put it into words. And I said to myself, I want to be part of that. That is the coolest thing. That's biology, it's also magic.
When you hold a living butterfly in your hand for the first time, maybe you've netted it or you've picked it off a flower or something, and here's this incredibly beautiful organism, intricately shaped with its feet and antennae and all these things moving at once.
Depending upon its species, a female butterfly can lay hundreds of eggs during her brief lifetime. Each initiates an extraordinary process of growth and transformation.
The eggs are remarkable in themselves. They have species-specific architectures, some of which are just astonishing. For instance, if you look at a monarch egg, it has a beautiful symmetrical structure. It looks like a little miniature dome or cathedral.
Ranging in size from a pinhead to the width of a child's fingernail, each egg is attached to a plant by an adhesive fluid secreted by the butterfly. They are lined with a coating of wax that helps keep them moist and viable. Each egg is deposited on a specific species of plant called a host. These host plants are the only source of food a butterfly's offspring will eat, so accurate identification of their leaves and branches is crucial, and the females are well equipped for the task.
The perception that they have of the odor of those plants is just overwhelming. So they can find those plants for miles and then Once it gets near its host plant, it can tell that the odor is getting stronger and stronger. Then it begins to focus on leaf shape. Instinctively, it knows what leaf shape its host plant has. And it begins to taste. And it tastes with its feet, with its forelegs. They drum the leaves, they scratch the leaves. And then they use their proboscis to taste the scratch. They also smell with their antennae. So they've got the legs, they've got their proboscis, they've got their antennae. They have all these mechanisms to make sure that it's the right plant. If it's the wrong plant, their caterpillars are going to die. Butterflies just don't make mistakes. I mean, it's just amazing. It's one of the greatest wonders of nature to watch how this female can do.
earthbound plant-eating arthropod with limited vision and mobility, into a beautiful winged insect that feeds on nectar, navigates with exceptional senses, and can fly 50 miles in a day, is truly a marvel of the natural world. Exactly how it happens is still very much a mystery. Yet innovative research at the level of molecules and cells provides intriguing new clues.
There is some continuity of tissues from caterpillar to adult butterfly, but most of what was there in the caterpillar is going to disappear and be turned into new structures that have no analog in the caterpillar. For instance, there's nothing like the compound eye of the adult butterfly present in the caterpillar. There's nothing like the proboscis present in the caterpillar, or the long articulated legs in the caterpillar. So these are all novel structures that are going to be built.
Photograph what's inside a chrysalis. That question was out there all along, and it occurred to me that magnetic resonance imaging might be perfect tool to use to see what goes on inside a chrysalis.
The challenge of visually documenting a butterfly's development led biologist Richard Stringer to Duke University and its Center for In Vivo Within the chrysalis, the proboscis developed as two separate pieces. Now, immediately following emergence, the butterfly must assemble them into a single unit, or die of starvation.
It's two half straws. There's a channel on one side and has to get it into the channel the other side. You'll see two little appendages on their head called palpi, and those palpi seem to protect the proboscis and help that proboscis get put together.
As the butterfly knits together the proboscis, its wings also take on their final structure.
When the butterfly comes out of the chrysalis, the wings are like velvet. They're soft, they're pliable. There's veins, the wings are filled with veins.
What the butterfly does is, using its abdominal muscles, pumps hemolymph fluid into the veins, into the wings, and they quickly expand to their full size and shape.
More than 100 species of milkweed grow throughout the United States during the spring and summer. It is the only plant a female monarch will select to host her eggs. Milkweed leaves contain cardiac glycosides, toxic chemicals that can cause illness or death. After hatching, the caterpillar eats the plants and stores their poisons in its outer layer of skin. Then during metamorphosis, the glycosides are transferred from caterpillar to adult. And whenever the monarch spreads its wings, their distinctive pattern sends a warning to predators. Don't eat me. I taste terrible. Like the monarch, milkweed cannot survive the harsh North American winter, and by the end of August, it goes to seed.
And at that point, the monarch stops all reproductive activity. If it's a female, no more eggs. If it's a male, no more sperm. They still feed, are active, but they show no interest in sex or reproduction.
With no milkweed for their eggs until spring, the monarchs devote themselves entirely to preparation for a transcontinental flight. They spend the final weeks of summer feeding on nectar to build reserves of carbohydrates and fats, the fuel for their journey. Monarchs born in the spring or early summer have a lifespan of only 2 to 4 weeks. But the generation that emerges in August is genetically programmed to live up to 9 months, a provision crucial to survival.
The last generation of the summer, the one that's going to live all winter and into the following spring, is really an interesting problem for biologists, because here you have 2-3 generations preceding that generation where the adult lives at most 2 weeks, 3 weeks, 4 weeks, and then dies. And now all of a sudden, a generation's produced that's going to live 9 months, 9 times as long. It's thought that there's a genetic difference comprised of about 6 genes that are unique in this generation that enable it to live that long.
Often called the Methuselah generation, their longevity will enable the butterflies to fly south for 8 weeks, endure 4 months of winter, and then start the return trip north to establish a new generation of monarchs in the spring. With the approach of autumn, the angle of the sun at midday drops below 56 degrees. The shortening days are the butterflies' cue to begin their migration. A network of In late October, on evenings following the passage of a Its mountains contain rich deposits of heavy metals that may play an important role in the monarch's navigation.
Gold, iron, manganese, copper, all of these metals created an anomalous magnetic field. And this seems to be important in bringing the monarchs in, because the monarchs have tiny particles of magnetite, the mineral magnetite, in their body at the base of the wing and in the thorax and abdomen. And these are believed to help them navigate to precisely this mountain range, because there's a very strong magnetic anomaly as one approaches this range due to all these heavy metals near the surface. So the particles of magnetite rotate like a little bar magnet inside a cell, and that cues the monarch that needs to head in a certain direction.
Until late in the 20th century, the only people to ever observe the butterfly's arrival in Mexico were the farmers and miners who lived and worked in these volcanic mountains. Since 1975, a dozen permanent overwintering colonies have been discovered in these mountains. Each maintains a critically balanced microclimate that helps sustain the monarchs until spring. Average temperatures in the colonies range from 35 to 60 degrees Fahrenheit, warm enough to protect the insects from freezing, and cool enough to minimize their expenditure of energy. For more than 4 months, hundreds of millions of butterflies live in a state of semi-hibernation while slowly consuming the reserves of nutrients they accumulated during the summer. The bark and needles on the fir trees provide stable footholds, and by flocking in roosts several layers deep, they can endure days
metamorphosis, their migration, their life cycle. How did this happen? How is it regulated? How is it controlled? This astonishing, remarkable transformation. A biologist who encounters a puzzle like metamorphosis is going to view that puzzle through an analytical filter, a lens. It's a way of trying to understand the problem. And for most biologists, that lens is going to be an undirected evolutionary process.
Since the late 19th century, most explanations for the life cycle of a butterfly or any other organism have shared a basic premise. To be considered scientific, they must rely exclusively upon undirected natural causes. This view was first published by Charles Darwin in his theory of evolution through random variation and natural selection. And today, it is widely accepted as a foundation of modern biology. But can such a theory account for the origin of metamorphosis?
On the evolutionary view of life, in particular on the Darwinian view of life, everything that an organism does, every feature that it has, all of its details ultimately relate But even if it were somehow possible, I don't think turning a car into a helicopter would be nearly as impressive as the actual transformation that takes place inside a chrysalis.
From the moment the chrysalis is formed, caterpillar tissues are destroyed and then recycled to help build wings, compound eyes, reproductive organs, and navigational systems of stunning beauty and efficiency. Yet despite the importance of cell death in the chrysalis, the origin of the process defies the basic logic of natural selection.
One of the fundamental requirements of natural selection is reproduction. You've got to be able to make copies of yourself, in particular of your genes. You've got to be able to pass them on. But a chrysalis, unless it represents a bridge to something yet to come, is really a casket. If you're a caterpillar, you're entering your own grave. Turning most of your body into a molecular soup would be suicide.
A caterpillar, unless it makes it through to the adult, is no good because it can't reproduce. You're not going to have offspring, and so you're a dead-end street evolutionarily. So it wouldn't be any benefit at all to kill yourself unless you've got a hidden plan up your sleeve. You know, like, okay, I know I can go ahead and commit suicide because there's a new me waiting to happen.
The caterpillar is not going to enter the chrysalis without simultaneously knowing, I've got a plan for getting out of this. I'm heading towards the adult butterfly. I'm going to reconstitute these tissues in the adult form, emerge, and go on my way. But that's not how natural selection operates. It can't look into the future and somehow anticipate what an evolving organism is going to need in a week or a month or 1,000 years from now. So if the first caterpillars were evolving into existence, without foresight, it's highly unlikely natural selection would retain a destructive process like cell death.
This absence of foresight is not the only challenge to Darwinian theory. Biologists have long recognized that natural selection cannot succeed by taking large evolutionary leaps. Instead, the process can only move forward through a series of small, incremental steps.
In evolution, it's the smaller scale changes that have a better chance of being passed on because they're relatively limited in their scope. That means they're disrupting less, and they're more likely to be tolerated by the organism. But when it comes to the origin of metamorphosis, the notion of gradual evolutionary change comes to a dead end.
By its very nature, metamorphosis is an all-or-nothing proposition. And throughout biological history, its success is hinged upon the immediate availability of a full set of instructions, including genes, proteins, and the developmental program required to integrate them.
It all has to be in place ahead of time. It needs to have the genes in place, the regulatory elements that are going to turn the genes on and off. It has to have all the cells pre-programmed to do what they're going to do when the time comes, so they respond to the signals they get in the right way. The larval cells have to know they're going to die. You got to remember the caterpillar isn't thinking about things. It's not saying, okay, now it's time to dissolve my epidermis, and okay, what about that gut? Got to get working on that gut. No, it has to happen rapidly and in a coordinated fashion. Once you're committed to the chrysalis stage, there's
not only challenges the Darwinian picture of life, in fact, it points in a positive way to the truth of intelligent design. If you saw a mechanical device of the sophistication of a butterfly, you would not for a moment hesitate to ascribe that to intelligence, because the butterfly is so much more sophisticated, almost beyond our comprehension, than anything that we make. Planning, foresight, artistry, engineering. Normally in our experience, when we see those criteria fulfilled, we see those indicators,